Who wants to get started basically explaining what are the main ideas of Einstein's theory, special theory of relativity? Or one main idea. We'll get started with that to get the ball rolling.
That in two frames of reference that translate that are okay, that this is so that the laws of physics that apply on one frame of reference will apply on another frame of reference that moves constantly with reference to the first one.
Right. So that's a basic hypothesis, a postulate that all unaccelerated frames are equivalent. Now, I don't believe, did Einstein in these references, I have printed one out. Let me just check. Okay.
That's the other paper, the first one.
Does Einstein actually define what are equivalent frames of reference?
No, that comes from the first paper. I not the one that was written by Einstein.
Well, both papers were written by Einstein.
Okay, so the first one, yeah. So yes.
Okay, so that's the online one. Let me.
Well, it's what you just said, Eric. It's that they're equivalent if they're not accelerating.
But does he, later in his work, he got into the question of rotation. Does he mention that these frames should not be rotating?
Yes, he does.
Okay.
He does, yes, he does.
All right. So that is the definition of what we today call inertial frames of reference.
Yeah.
Not accelerating and not rotating. Okay, so that's one hypothesis. What is a second postulate that he uses to then actually derive special relativity? Sam?
The speed of light is the same in all.
Okay.
That's what I was going to say.
Frames of reference.
Yeah.
Right.
Yeah, the incompatibility of light speed with classical mechanics.
Right. So, and where does he get that second hypothesis from? What inspires that second hypothesis?
Through the addition and subtraction of velocities to define velocities from in one frame of reference from the other frame of reference.
Well, no, that's something that can be derived, that he does derive from the hypothesis that the speed of light is constant in all frames of reference. But where does he get that hypothesis? What inspires that?
Is it something to do with putting labels on Branston pickle bottles?
What?
What?
Was it the FISO experiment? The light traveling through the liquid? Or is that just the experiment that confirmed his theory?
Well, there's basically two things. Does anybody want to propose either one? One theoretical and one experimental.
Well, that's how Sam says the experiment of Fizeau. He proves that was light in moving water, and that the velocities don't add up. Velocities don't simply add in relativity.
But there's something more on the theoretical end. There's something that was much better known and that we had studied.
Did it have to do with space?
or mass.
What is at the time Einstein was writing, what was the mathematical theory of the propagation of light?
Yeah, the model of I should remember Maxwell
Right,
equations.
right. The basic, framework developed by this time 40 years earlier and perfected, in the intermediate, perfected by about 10 or 15 years before 1905 was Maxwell's theory of electromagnetism. And one of the biggest, most outstanding contribution of Maxwell's theory was his realization that light and many other phenomena discovered later in the 19th century, such as X-rays and ultraviolet and so on, were all electromagnetic waves. And that discovery was in part inspired by his knowledge that the speed of light that had by then been experimentally measured was numerically identical to a constant that arose from measuring electromagnetic phenomena. And therefore, he hypothesized that that constant was the speed of light, and that the connection between electricity and electric fields and magnetic fields could express by equations whose unique constant was the speed of light. So that meant from the time of Maxwell on, you have a speed being embedded in the laws of electromagnetism. And it became evident when physicists thought about that, that if light was carried by a hypothetical substance, that is, that these electromagnetic waves were oscillations in a hypothetical substance, which in English was called ether, you could measure the speed that the Earth was traveling relative to this ether. And of course, this was the famous Michelson-Morley experiment, which determined that you could not do that. And that was experimental verification. A number of scientists realized, starting with Lorentz, that was experimental verification of what was evident theoretically in the equations themselves, that the speed of light would be a constant, no matter where it was measured from and who was doing the measurement and what astronomical body they were placed on, that would always be a constant. And that was the confirmation in the Michelson-Morley experiment. So, we have a historical development, which Einstein, gives due credit to. But starting with Lorentz, you have the realization that on both theoretical and observational grounds, the speed of light must be a constant. And B, that implies that modifications have to be made to Newtonian mechanics. So Lorentz was the first start making those modifications. And relative to Lorentz, basically what was Einstein's, those equations already existed. What was Einstein's basic contribution in developing the special theory of relativity? According to Einstein.
I mean, was it to like relate those same transformations from electromagnetism to like, wasn't it to just like any law of nature must satisfy those transformations? So like took it from the world of the electromagnetic.
Anybody else? Well, let me give you a hint. Was there another postulate that Einstein used to mathematically derive the Lorentz transformations?
The Galilean system of coordinates? There's the Galilean transformation. Oh,
The definition.
The Galilean transformation is
The definition.
Newtonian is the non-relativistic.
right.
Are you referring to the definition of simultaneity that he uses?
Right. Exactly.
Mhm.
So those, would you elaborate? What was his definition of simultaneity?
That the simultaneity between the two distant events has to be defined by using what is it, synchronous clocks through via light signals.
Right. So by defining, and he made clear this was a definition, simultaneity as simultaneously receiving, an agreed to light signal at two different spots, then the accomplishment of special relativity was to show that the Lorentz transformations are a mathematical consequence of those three simple hypotheses. That the speed of light will always be measured as, this is like any good scientific statement, it's a prediction. It predicts that anyone, anywhere measuring the speed of light will always get the same answer. Two, that all inertial frames are equivalent, and they're in all scientific ways, and therefore are also equivalent in the question of the speed of light. And three, the definition of simultaneity. And he shows that from those three hypotheses, you can mathematically and just by using simple algebra, obtain the Lorentz transformations. Now, in his view, and in my view, this actually is a pretty, once you read the texts and ignore the equations, I think this is a pretty intuitively clear description. Do you?
It is.
Did the description that he made of how this is derived, again, ignoring the equations, does that make sense?
Yes.
Yeah.
Yeah, it seemed very just like observation only based. Like,
Well, it was observationally based, but you have the only non-intuitive element, which you just have to accept because it's a definition, is the definition of simultaneity. That he was saying that the way you, not the only way, but the way you can synchronize clocks is with light signals. And once you accept that clocks synchronized in that manner are synchronized, then it follows, which is certainly non-intuitive, that that definition of synchronization does depend on your frame of reference. So that while the speed of light is the same in all frames of reference, the statement, this clock and that clock are synchronized, is not the same in all frames of reference. And the mathematical way, right? Well, what are the most important conclusions he draws from that relate to the previously discovered Lorentz transformations? What are the what seem to be surprising consequences of these intuitively simple
Well, like
Was
time
one
dilation and
what?
time dilation and
time dilation and the relationship between energy and mass?
Right. And the other one that seems strange.
This,
Is it four-dimensional space?
All right.
That's kind of
Well,
time dilation.
we'll get back to that. But
sim-
the other Lorentz
simultaneity- that
Lorentz
simultaneity is relative.
transformation. Well, I don't know. I'm sure you all know it. It's the Lorentz contraction.
actually,
Yeah,
sorry, yes, I was
but,
just trying to say that.
The main idea is that simultaneity is relative and that length and time change with motion.
Right. And of course, Einstein, for the first time, goes from those equations to the equivalence of energy and mass. At high velocities, the mass of objects as measured in a given frame depends on their relative velocity. And that's very important.
I have a question there with
Yeah.
mass, because it's inertial mass, the one that changes, right?
The, well, as opposed to gravitational mass, what are you asking?
No, I mean, from the reading of the two papers, I seem to gather that the mass of an object is the mass at rest, the inertial mass. So there's more than one component to mass.
Well, yes, but rest mass means what it says. So if you are at rest, or the object is at rest relative to the observer, the mass is a minimum, and that's called the rest mass.
Okay. So when you accelerate an object, part of the energy, the energy that goes into the object to accelerate the object, there's a part of that energy that actually increases the mass of the object. With reference to the
Right.
the inertial frame of reference.
Right. So that's right. So the inertial mass becomes different than the rest mass. Now, at rest, those are identical. The inertial mass of an object is the rest mass if you are measuring it in the frame at which the object is at rest. So as the difference between you and the object increase, then the inertial mass of the object also increases. And that's a very important concept, because that means that when you say a particle or an object has this much energy, that statement always has to be related to your frame of reference. So normally when we talk the energy of this cosmic ray is 1 billion electron volts, we're normally assuming that that's in reference to the lab reference. So the lab reference is, wherever you're measuring,
Yeah.
which is convenient because we know that laboratories on Earth, even though they are moving relative to each other, obviously, a laboratory in Australia is moving relative to a laboratory in Middlesex, New Jersey, because one is rotating this way and the other is rotating that way. So obviously there is a difference, but this difference is so tiny compared with the speed of light that it can almost be ignored. And therefore we can say wherever we are on Earth, it's the lab frame of reference.
So you
But that particle, in other words, what was I having this discussion with? I forget. Oh, yeah.
The Doppler effect is negligible.
Right. So you can have a frame of reference. And in some cases, this is useful, that is fixed to the particle. And the Earth is moving with, at the speed of light, near the speed of light relative to this particle. If you're interested, for example, in the interactions that this particle has when it hits the atmosphere. So all of that, so energy is not, the idea of a conservation of energy is only valid when a frame of reference is specified. The equivalence of mass and energy, the conservation of mass energy, right, the conservation of mass plus energy is an absolute conservation law, independent of your frame of reference.
Can you repeat that, please? The conservation of the...
So in the old dynamics, pre-relativistic or non-relativistic, you had two separate conservation laws by the time of 1905, which was the conservation of mass and the conservation of energy. And what Einstein showed was that those laws can only be interpreted in terms of a specific frame of reference.
Yes.
But if you combine them with his famous equation, E equals mc squared, and the sum of energy and matter, with matter multiplied by the very big constant, the square of the speed of light, that would be valid, independent of your frame of reference.
Yes, because actually EMC squared is already a simplification of the other equation that includes the Lorentz transformations within.
Right, right. He showed that you could derive one from the other, from the what we today call, I don't think he refers to it as that, as the gamma factor. So the gamma factor is the simple algebraic expression, the square root of 1 minus v squared c squared.
Peter, can you mute yourself while you're not speaking, because your chair makes a lot of noise? Thank you, Peter.
Okay.
Yeah, okay. Yeah, the gamma factor, yeah, square root of 1 minus v squared over c squared.
Right. So in practical terms, going forward in the history of physics, what were the most significant implications of Einstein's special theory?
the notion that clocks that you need to account for the motion of clocks when you need to use simultaneity, for example, for satellites and stuff like that.
Right, although that really doesn't come into account for another half century, because we didn't have satellites until 57. So that's a half century. There was much more immediate consequences in the history of physics.
Well, the energy mass relationship
Right.
kind of leads you into the development of the bomb, right?
Well, it's much earlier than that. Remember the historical context. We had just discussed in the last classes the more or less simultaneous discovery of X-rays and radioactivity and radioactive isotopes.
Mm.
On the Maxwell-Hertz, you're talking about the Maxwell-Hertz equations.
No, I was talking about in the last class the last study group, we were talking about in 1895, so this is only a decade before Einstein's paper on special relativity, you have Röntgen's discovery of X-rays, Becquerel's discoveries of radioactivity, and the Curie's discovery of these various radioactive materials. So when you put these things together, I don't think we've gotten to the discovery of the nucleus, did we? I don't think we discussed that.
No, I don't think.
But that's so the discovery of the nucleus is what, 1915? I'm forgetting my own. Let's see.
Yeah, I don't remember.
I have to go back to.
That was 1911.
Okay, yeah, 1911
Was
close
the
enough.
gold
So
foil
this is
experiment.
very soon. This is only 6 years in the future when the special relativity. So all of these things relate to the nucleus, which people didn't know existed. Something that in linear size was far smaller than the atom, although contained almost all the atom's mass. And Becquerel and the Curies had already commented on that this was a source of energy orders of magnitude greater than chemical energies. And that meant that the E equals mc squared law allowed people to study nuclear energies in part by simply accurately measuring the mass of the nuclei of various elements, because they already knew that when nuclear reactions, radioactivity, other transformations that involve the nucleus led to what was now a measurable decrease in the mass of the products, that had to indicate the release of that much energy by equals mc squared. So this was an extremely timely discovery, and you can see by its history that it was a discovery whose time had come. Einstein was the one who put this discovery into a neat and intellectually satisfying package. But you could see by the names involved, Lorentz, Minkowski, Einstein, and Poincare, many scientists, a number of scientists, were converging in the same direction because this was a consequence of both the perfection of the development of Maxwell's electromagnetic theory and these experiments that had confirmed the constancy of the speed of light. So this is basically something that clearly, if Einstein hadn't existed, we would still get maybe a few years later the special theory of relativity. And it would arrive in time to be useful for the nuclear development of nuclear physics. So you can see that this conforms with the model of evolution of science as a collective activity in which obviously people's unique creativity can accelerate this process. But in general, we've seen, especially in this revolutionary period, that this is a convergence of several scientists coming up with similar ideas based on their interactions with each other. So Einstein, of course, was aware of Lorentz Poincaré's previous work, and Lorentz gave due credit to Einstein in pushing that work forward. Our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy and a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks. Sam, did you want to say something else?
No, I was just gonna say, so Einstein wasn't really all that.
What?
I was just joking. I was saying, so Einstein wasn't really all that.
Well, as I say, first of all, Einstein, and this is his own words, was formulating a way of understanding these equations that was very useful to pushing physics forward. What he's called the heuristic value. Heuristic is basically the educational value of the special theory of relativity. In Einstein's view, and this was the dominant view of scientists, of physicists, all the way up to the last half century or so, is that the equations alone don't constitute physics. You have to have a way of understanding essentially an image that shows how these equations derive from physical processes in the universe. And he was providing that image, that structure, in terms of these very simple and intuitive, well, you want to say they're intuitive or not, easy to understand postulates. So while the equations, Lorentz transformations, had already existed, Lorentz himself did not have a clear idea of where did these equations come from. But Einstein provided that. What I'm saying is that structure was pretty much coming out of the collective work of, several scientists, and was feeding almost immediately into the collective work of the other group of scientists that were, including Einstein himself, that started to work on the problem of the nucleus and nuclear energy. So let me now say, given all this, are there things that you don't feel you understand about special relativity? And by the way, I should just say, because of my commitments, we're going to have to make a hard cutoff at 4 o'clock. As in the past, we can always continue these discussions to the next session. We're not under any divine commandment that there's a one-to-one correspondence between these topics and the sessions.
So I have a question going back to the heuristic value of the theory of relativity, that there's something in the key principle, as it says, what I took note is this: the laws of nature must be covariant under Lorentz transformations. And I understand the principle of covariance, but what does it mean? I mean that the laws of nature must be covariant, that if they transform through a covariance matrix, they will be equivalent after the transformation, and keep their relation to each other through different frames of reference.
It really is just a mathematical way of saying that just as without going through any of the analysis, you can mathematically prove, if you have the, matrix manipulations in your mathematical skill set, that if you apply the Lorentz transformation to Maxwell's equations, you will get Maxwell's equations back. So that's what it means, covariant.
Okay.
You can express the Lorentz the Lorentz formula as a transformation of coordinates. So remember, we have time proceeding differently and length in the direction of motion. And that's very important. When we talk about Lorentz contraction, we're talking about a unidimensional contraction. This only applies in the direction of the relative motion between you and the object. Doesn't apply in the two perpendicular directions. So you can express these equations as a transformation of the way you're measuring the dimensions. And if you apply that, so you can express that mathematically as a matrix, and if you apply that matrix to Maxwell's equations, you get back Maxwell's equations. So when he's saying, when Einstein writes, any law of nature must be covariant, he's saying that when you express that law of nature mathematically, whatever happens, it has to have the same property that if you apply the Lorentz transformations, you get back the same equation. So that's what covariance means. So if you write down, you're saying, I mean, this is not a disrespectful statement. This is simply a statement of fact. But the fact is, I receive, on average, 2 complete theories of the universe per week, roughly. And one guy got really enraged when I told him this. But that's the reason I can't reply to these people. If I replied to them, I wouldn't do anything else. But some of them are insulted when I say, well, I get 2 of these a week, so I can't reply to you. But all of these people, if they knew enough mathematics, and many of them don't know much mathematics, could see whether their law of the universe even was possible to be valid Einstein would say, well, first see whether it's Lorentz invariant. If it is, throw it away.
Yeah.
Now, of course, you can write an infinite number of equations that are Lorentz invariant, which are all wrong. They don't.
Yes.
They are not a description of the real universe.
Yeah.
But what he's saying is you can't do the converse. You can't write an equation which is a description of the universe that violates Lorentz invariance.
Yeah.
And that's, well, we'll see whether we have time. Well, actually, I'm going to leave that, elaborating that to a future class. But that certainly is an important criterion. I mean, there are other criterions. One of my favorite is dimensional analysis. If you write an equation and it says, you know, when you work out the equation, it says 30 centimeters per second is equal to 14 centimeters. You know that you've made a mistake.
Yeah.
Because the dimensions, and this
Yeah.
fortunately is a bit different terminology for dimensions. It's not referring alone to length and time, because your dimensions might involve mass or other things.
Yeah.
But those dimensions have to be the same on the two sides of the equation. Otherwise, you can again throw that equation out.
Yeah. Yeah.
You derived it, you made a mistake, and you have to go back and find
Yeah,
out.
when I studied engineering, we call that units. I mean, the units have.
That's unitary analysis is
Yeah.
exactly the same as
Yeah.
dimensional
Yeah,
analysis.
on both sides of the
It's just a
equation, actually
synonym.
the same. Yeah.
Yeah. And it's really useful to catch
Yep.
errors because, yeah, even with today's software, if you do a derivation that involves 10 or 15 steps, it's easy to make an error somewhere in them.
Yeah.
All right. Any other puzzles about relativity? And then I'm going to ask a few questions. All right. So if we look at the popular notions of relativity, and in this case, something that corresponds to Einstein's own notion, philosophical notions, does special relativity, which describes the universe in 4 dimensions, 3 space dimensions and a time dimension, does that imply what's called a block universe? In other words, a block universe is a universe that you could visualize as a single block in these 4 dimensions, implying that the future exists equally as the past and the present, and therefore the future is totally determined. Does special relativity imply a block universe? And if not, why not? And as I say, not only is this a fairly common popular interpretation, it was Einstein's interpretation. And there is the famous quote that he wrote to the Greek wife of his best friend who had just died. And he wrote, "To us confirmed physicists, the past, the present, and the future are but an illusion, if a persistent one."
Yeah.
So, yeah, discuss.
No, based on that, I would venture to say that yes, that it implies the existence of a block universe.
Why?
That's a good question. Because in the equations there is not an arrow of time.
Right.
The equations are symmetrical, and therefore you can reverse them, and so yeah, to me special relativity does imply a block universe, but maybe I'm wrong.
Well, if we go back in time a few classes, we discussed thermodynamics. And we got into the question of the implication of the second law of thermodynamics, that real processes in the universe are irreversible. In other words, that there is a direction to time, and that there is a intrinsic difference between the past and the future. So, does special relativity contradict the second law of thermodynamics?
I don't have an answer for that. Yeah, in the equations I read, I don't see the second law of thermodynamics implied in them. Maybe I don't see them because I don't know enough mathematics.
Well, as I say, let me say that this is a problem that occurred to physicists, and we're not going to get to the resolution. Although in the class on the second law, I did sort of imply what the resolution of these contradictions are. Chronologically, we're not going to get to that until we get up to the 1960s. So this isn't a trivial question. And in the view of many physicists today, I would say that they'd say it's unresolved. Although
I would have a question for you.
Yeah.
I have a question. Would this is on kind of a tangent or different subject, but I was thinking of it before you got this far with the conversation. Is this then philosophically would be a contradiction to theological teaching on free will? It could be incompatible with theology of doctrine of free will. Could be incompatible.
Well, I don't think the theologians agree on what doctrine says about free will. So I don't think there is one theological notion of free will. But certainly this gets into the question of determinacy. So determinacy, and as we get into the development of quantum mechanics, we're going to get into more precise definitions of this term. But in 1905, we're before the full development of quantum mechanics. Quantum mechanics, as we just discussed, is just starting to develop. So setting aside those questions, determinacy in the sense that Laplace first formulated it long before Einstein is the notion that if you know everything about the universe today, then you can predict its future.
Mm.
So that's the what you would call hard determinacy or extreme determinacy. When we get into quantum mechanics, there's a much more narrow definition, which is all events in the universe are caused by previous events, which again becomes called into question in the philosophical discussions of what the equations of quantum mechanics mean. But what I'm raising here is, does this notion of a four-dimensional universe contradict what people already knew of the irreversibility of processes in the universe from the second law of thermodynamics?
Can you comment?
Yeah,
Can you comment on the elemental table and whether this is confirmed or the deterministic view?
Go ahead.
Oh, the elemental table. Can you comment on, has this as we hear of the new elements, they're confirming the deterministic conclusion?
Well, you're referring to the periodic table of the elements, right?
Yes.
I don't understand the question. What does the periodic table of the elements have to do with?
Well, does the results of new elements being added to that, is that to confirm the conclusion of a deterministic?
No, I mean, again, this is just other examples of the irreversibility of processes. As scientists studied nuclear processes, they realized that just like chemical processes, they had a direction of evolution. Eventually, by the 1930s, scientists such as Hans Bethe had discovered that elements were produced by fusion processes in stars. But this, again, is an irreversible process. It's not irreversible in the case of a given ion, who can actually do things to iron to make it go back to split it apart. But thermodynamically, it's irreversible that these processes tend to go in a certain direction. That has led to all these wonderful elements that we have. And the reverse, breaking the elements down back to hydrogen, is a process that goes exponentially much more slowly. And therefore, you do have an evolution in the chemical composition of the cosmos, just like, people realized at the time of the second law of thermodynamics that there's a one-way evolution to chemical reactions. And to reverse them, you have to input energy. Well, I'm going to cut this off. I'll just say, spoiler alert, the answer is
I think the answer is no.
What? The answer is
I think the answer is no.
Yeah, so Einstein was definitely, and subsequent science showed why, wrong in thinking that the ability of four-dimensional equations to describe physical processes, that does not imply the big block universe, which is equivalent to Laplace's.
I mean, isn't it precisely because you have a coordinate which is time which is variable, mean that the universe is not instantaneous?
Well, I mean, I'm not going to give away the answer because I want people to think
No,
about
but
it. To a certain extent, I gave away the answer when I was talking about the second law, so you can go back to that. But there is a clue in why the block universe, there is a mathematical clue in why the block universe is wrong, which is that the four dimensions are not treated mathematically the same. There is a minus sign, square root of -1 in front of the time dimension.
Yes.
So the time dimension is described in terms of what mathematically are called imaginary numbers. Now that imaginary term is purely historical. There's nothing imaginary about imaginary numbers. They're just as good parts of mathematics as quote unquote real numbers. But it is a clue that time is not quote unquote just another dimension, that it does not have the same relation to the three space dimensions that the three space dimensions have to each other. It has a different relationship. So that's one clue. But it has nothing to do, well, I won't say nothing. But there's another, well, I will give a clue.
Minkowski
What-
space-time.
What subsequent physicists, scientists concluded was that Einstein was making an unjustifiable abstraction from reality. And physicists have to make abstraction from reality to describe reality, because reality is infinitely complex. But you can make justifiable abstractions and understand the limit of those abstractions. But if you make one implicitly, that is, you're making an abstraction from reality and you don't know that you're making it or you don't acknowledge, then you can end up with the wrong conclusions. And in going from special relativity to a block universe, Einstein made a very important abstraction from reality, which wasn't pointed out until approximately 60 years later, in the mid-60s. But we will discuss that going forward. So I'll just leave that for the future. Now, one big implication of special relativity that we haven't discussed, but is very important in popular culture and in technology, is what? What is a big implication of special relativity that we didn't mention? Hint, a limitation.
Something about the limitation of the velocity, critical velocity of a particle in motion. Like something can only go so fast.
Right. Well,
It seemed related to, like, because it had something to do with the,
to finish the sentence, something can only go so fast. What is the so? So fast being what?
is it the speed of light?
Right.
Yeah. Yeah.
So that's a big implication and obviously a technological limit. Because if the speed of light is and by the way, you really should say the speed of light in a vacuum, because scientists at the time knew that light travels slower in all mediums than the speed of light in the vacuum. So it is possible in a given medium for an object to travel faster than light in that medium. And with the development of better and better instruments, people actually use that as a measurement technique, because in a medium, such as a gas or a fluid, highly energetic particles can exceed the speed of light in that medium, which is defined as the speed of light in a vacuum divided by that medium's index of refraction. And when a particle exceeds the speed of light in a medium, it produces a phenomena very similar to a sonic boom when an object exceeds the speed of sound in a given medium. And you get the phenomenon of Cherenkov radiation, which is a good way of measuring fast-moving particles. But the speed of light in a vacuum appears from the Lorentz transformations to be a limiting speed, because light cannot travel faster than that, because light always travels at the same speed. And particles, as they approach that speed, their inertia increases without limit. So it takes the amount of energy to reach the speed of light for a massive particle is without limit. So you can never reach the speed of light because it would take an infinite amount of energy, which is impossible. And the equations, of course, themselves don't make any sense, because the Lorentz transformation becomes imaginary.
Imaginary.
So that's a big technological limitation, because travel to other planetary systems, to other stars, the stuff of science fiction and, many speculations, does not become impossible, but it certainly becomes very difficult when it takes a few years to reach the nearest star. Now, our ancestors took a few years to reach their destination when they were using the initial version of transoceanic ships, but it still becomes pretty inconvenient, especially if you have to reach beyond the nearest stars. So that is a clear consequence of these simple postulates. And because it's a clear consequence of these postulates, it is really difficult to get around it, to even think of a theoretical way to move faster than the speed of light. Our videos come out of LPPFusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description, and thanks. As a fun exercise for the next class, I will say, are there ways to develop in the distant future, a galactic society like is beloved of all science fiction without exceeding the speed of light?
Yes.
Okay. Well, we'll leave the elucidation of how you would do that for the next class.
Can we get a hint?
What?
Can we get a
What?
can we get a hint? Or at least an area of
No, I don't think you need a hint.
Cryogenic.
Use generational chips.
How about cryogenics?
But
Use generational chips.
anyway, I'll make one concluding point, which is Well, again, I'll put this as a question. Here we are 120 years later. What are the main technologies that employ this discovery, that employ special relativity?
Mhm.
Let's give some examples. We've given one example, which is
The bomb,
the what?
the nuclear bomb.
Right. Clearly, the study of nuclear physics and all the technologies that derive from it, including our studies of fusion energy, all involve special relativity, especially the transformation of energy into mass, which makes sense of nuclear reactions. And also the question of the change in inertial mass becomes important, excuse me, at relatively low energies when you're talking about electrons.
Mhm.
Electrons become relativistic as you approach 500 keV. So that's 500,000 electron volts.
Mhm.
And to present day technology, that's really quite a low energy. And it's a low energy relative to nuclear reactions, most of which liberate millions of electron volts per particle.
Mhm.
So everything nuclear involves special relativity. The
Everything
second
that can-
example, which I think, what?
Microwaves devices?
Positioning systems, GPS, anything that
Yeah,
is
GPS.
satellite-based and needs precise timing, needs uses Lorentz transformations to correct for the time contraction or dilation.
It is very easy with GPS precision, which I forget what the precision needed is, but I think it is in well, no, we can figure it out. The speed of light is 30 centimeters per nanosecond. So obviously, to localize yourself to the extent GPS does, you need nanosecond precision, synchronization. And if you do the arithmetic with 1 minus v squared over c squared, and you put in the velocity of satellites, it becomes clear that it's very easy to get transformations that would annihilate that precision. So you absolutely need that for GPS positioning and all the other technologies that rely on precise synchronization. Nanoseconds is pretty much the time scale that all of our electronic devices operate on now, and a little beyond, because as you'll see if you glance at their labels, they talk about how many gigahertz they operate on. So of course, our devices all have to be synchronized internally and with each other on nanosecond time scales. So this again involves that they have to have, when they're detached from, when they're reliant on electromagnetic waves to synchronize themselves, they have to be reliant on a frame of reference that takes into account things to the level of, that takes into account the Lorentz transformation. Okay. So why don't you all think about that? I don't know where we're going next, but it's probably into the early stages of nuclear physics, because 1911 is soon after 1905. And Sam is hereby responsible for reminding our broader audience that they have to do their reading and that the session is next week.
It's next week?
No, I mean, that's when the reminder is it's relative to the frame of reference. The reminder that you're responsible for sending out is going to go out a week before whenever we schedule the next study group,
Okay, I got it.
Yeah,
which depends on my time. So I'll tell you all when
that's cool.
I'm ready to send out a new one.
We know you're busy.
All right. Okay, so hopefully it'll be today is the 25th. If it isn't in June, hopefully it'll be in early July. June is busy because we're really trying to get this breakthrough in the lab. And then we're going to have an exciting public cosmology workshop in Portugal,
Mhm.
which is being arranged by the Demystify Science podcast and financed by a Silicon Valley type.
Ooh,
We might have a Silicon Valley type on our side. Now that,
wow.
That will be
Time
great.
to finally get some VC funding into
yeah, right. Well, it's
get some of that tech money.
certainly something that will come up. And speaking of schedule, just review, Sam, did you say that you're going to be absent the next 2 weeks?
Yeah,
Friday?
yeah, next 2 weeks.
Okay. And as long as I've got you, this is irrelevant, but can we set a deadline of next week for a draft of the Unity website?
Yeah, I can try and have something to look at.
For a week today?
Yeah.
Okay. All right. Well, I got to run, so I'll sign off and everybody have a good rest of the weekend celebrating. In the United States, we can celebrate militarist imperialism tomorrow. And hopefully you guys have something better to celebrate in other.
We'll just dance around a maypole.
What? What did you say? Oh,
We'll just dance around.
right.
Dance around the maypole. May Day.
No, here it's Memorial Day.
Peter, are you in Canada?
What?
This is a question for Peter. Peter, are you in Canada?
No, I'm in the UK.
Oh, okay.
Yeah. Now, nobody celebrates Memorial Day, I think, except in the United States. One of our many militaristic celebrations. But okay. Take
Cool.
care then. I'm signing off.
Thanks, Eric. Cheers. Thanks all.
Cheers.
Bye.
Cheers. Bye.
Ciao.